Today, we're going to talk about the most ambitious thing our species has ever seriously considered doing. Not visiting another planet, not building a space station, not even establishing a base on Mars, but leaving our solar system entirely forever and never coming back. Not as a thought experiment, not as science fiction, as a plan. Because here's the thing that tend to get lost in conversations about space exploration. The question of whether humans will one day travel to another star is not purely a technological question. It is also a question of time and patience and what we are willing to sacrifice, not us personally, but the generations that come after us, generations who will be born on a ship, live their entire lives on that ship, and die on that ship, never having seen Earth, never having felt real sunlight, never having stood on solid ground that wasn't engineered by human hands. That is what an interstellar colony actually means. And tonight, we're going to walk through every part of it, the physics, the biology, the engineering, the psychology, and the philosophy, as honestly and as carefully as the science currently allows. No exaggeration, no hand-waving, just a real picture of what it would take. Let's start with the question that makes everything else make sense. Why would we leave? It sounds dramatic to even ask. Earth is, as far as we know with complete certainty, the only world in the universe currently confirmed to support complex life. It is warm. It has liquid water. It has an atmosphere with the right mix of gases. It has a magnetic field that protects us from the worst of what space sends our way. We evolved here over hundreds of millions of years, and every single system in our bodies is calibrated to function in exactly this environment. So why would anyone seriously propose sending humans to a point of light 4.2 light years away, a distance so vast that there's almost no meaningful analogy in everyday experience? The answer, when you look at it clearly, is not optimism. It is something closer to long-term risk management. In 2021, a peer-reviewed paper published in the journal Acta Astronautica laid out what the authors called a window of peril. The argument being that since the mid-20th century, humanity has possessed the tools to cause its own extinction, and that window will not safely close until our civilization exists in more than one place. The specific threats the paper identified were not exotic. They included nuclear conflict, engineered pandemics, and large-scale ecological collapse. None of these require science fiction to imagine. All of them are, in principle, capable of ending not just civilization, but the species itself. Stephen Hawking made a similar argument in 2017, stating publicly that he believed human population pressure and increasing energy use could render Earth uninhabitable within 600 years. That is a specific, falsifiable claim, and it is worth noting that many scientists consider 600 years an overly pessimistic timeline, but the underlying logic that a civilization confined to one planet is inherently vulnerable to extinction in a way that a multi-world civilization is not, is taken seriously in academic literature on long-term human survival. The point is not that we are definitely doomed. The point is that spreading to another star system is the only form of insurance that covers all possible scenarios simultaneously. A backup colony 4.2 light years away cannot be destroyed by anything that destroys Earth, because the two systems are causally disconnected on any timescale relevant to the threats we are discussing. That is the rational case. There is also a different case, which is harder to quantify but perhaps more honest. That exploration is something humans do. That curiosity is not a luxury, but a defining characteristic of our species, and that the stars have represented a boundary worth crossing since long before anyone could articulate a survival argument for doing so. Both of these things can be true at the same time. But before we talk about the journey, we need to talk about the destination, because another star system is not specific enough. For an interstellar mission to be more than an abstract concept, it needs a target. And right now, in 2025, the most seriously discussed target is a planet called Proxima Centauri b, the closest candidate. Proxima Centauri is the nearest star to our Sun. It sits at a distance of approximately 4.24 light years, which sounds manageable until you convert into kilometers, at which point it becomes 40 trillion kilometers, and the number stops being useful to the human brain. We will come back to the distance problem in detail shortly. For now, What matters is that in 2016, a team of astronomers confirmed the existence of a planet orbiting Proxima Centauri within its habitable zone, the band of distances from a star where liquid water could theoretically exist on a planet's surface. This planet is Proxima Centauri b. Its minimum confirmed mass is approximately 1.3 times that of Earth, which places in the category of rocky, terrestrial planets rather than gas giants. It orbits its star at a distance of roughly 0.05 astronomical units. Far closer than Mercury orbits our Sun, but Proxima Centauri is also far smaller, cooler, and dimmer than our Sun, which means the energy budget at that distance is actually within the range where liquid water is not impossible. That last sentence was carefully worded, because here is where we need be precise about what the science actually says versus what gets reported in popular coverage. Proxima Centauri b is not confirmed to be habitable. It is not confirmed to have an atmosphere. It is not confirmed to have liquid water. What is confirmed is its approximate mass and orbital parameters, and the fact that its orbit falls within what astronomers call the conservative habitable zone. Everything beyond that is currently a matter of active scientific debate, and the debates are genuinely unresolved. There are at least two major scientific camps on the question of Proxima b's habitability, and neither one has definitively won the argument. The first camp raises serious concerns about the nature of Proxima Centauri itself. Proxima Centauri is an M-dwarf star, a red dwarf, and M-dwarfs are known to be significantly more active than our Sun, particularly in their youth. Proxima Centauri regularly produces powerful stellar flares that release intense bursts of X-ray and ultraviolet radiation. Studies have calculated that Proxima b currently receives roughly 30 times more extreme ultraviolet radiation than Earth receives from the Sun, and approximately 250 times more X-ray radiation. The argument from this camp is that this radiation environment, sustained over billions of years, would likely strip away any substantial atmosphere the planet might have had, leaving it as an airless, radiation-scoured rock, inhospitable to life as we understand it. The second camp argues that this conclusion is not inevitable. They point out that Venus, for example, has no global magnetic field and is bombarded by the solar wind, yet maintains a thick atmosphere through geological processes, volcanic outgassing, and other mechanisms that continuously replenish what is lost. If Proxima b is geologically active, it might be doing something similar. More significantly, a 2025 study suggested that Proxima b may possess a magnetic field generated by a liquid iron core, similar in structure to Earth's magnetosphere. If that is confirmed, it would dramatically change the habitability calculus, because a planetary magnetic field is one of the primary mechanisms by which a planet retains its atmosphere against stellar wind erosion. It is also worth noting that some researchers have proposed a scenario called a habitable evaporated core model, in which Proxima b originally formed with a hydrogen envelope that was stripped away early in the star's history, but a volatile-rich rocky core survived beneath it and eventually developed a secondary atmosphere through outgassing. This is a real hypothesis with real scientific support, but it remains a hypothesis. A 2024 study published in the monthly notices of the Royal Astronomical Society added another layer of nuance, finding that ozone, if present in Proxima b's atmosphere, would significantly affect the planet's temperature distribution and atmospheric circulation patterns. This matters because ozone is also a key shield against ultraviolet radiation. The presence or absence of ozone in the planet's atmosphere will be one of the key discriminators between a habitable world and an uninhabitable one. The bottom line, stated as clearly as current science allows, Proxima Centauri b is the most plausible interstellar destination we have identified. It is the closest. It is the right size. It is in the right orbital position. Whether it is actually habitable is genuinely unknown. Any mission plan that assumes it is habitable is making an assumption, not a verified fact. And that assumption would need to be resolved, ideally through remote observation before any crewed mission departs. This is not a minor detail. It is the central uncertainty around which the entire mission concept is built. We would be sending people on a journey of potentially thousands of years toward a world that we do not yet know can support human life. Now let's talk about the distance, because this is a part that tend to be stated and then immediately moved past. And it shouldn't be, for 0.24 light years. A light year is the distance light travels in 1 year, moving at approximately 299,792 kilometers per second. In 1 second, light travels a distance roughly equivalent to 7.5 laps around the Earth's equator. In 1 year, at that speed, light covers approximately 9.46 trillion kilometers. Proxima Centauri is 4.24 of those years away. The fastest human-made object ever launched is the Parker Solar Probe, which at its closest approach to the Sun reaches speeds of approximately 690,000 kilometers per hour, or roughly 192 kilometers per second. That is genuinely extraordinary by any human engineering standard. The Parker Solar Probe is the fastest thing we have ever built. At that speed, a journey to Proxima Centauri would take approximately 6,300 years. Let that number settle for a moment. 6,300 years. That is longer than the entirety of recorded human history. The pyramids at Giza were built roughly 4,500 years ago. Rome at its height was roughly 2,000 years ago. Writing itself was only invented approximately 5,000 years ago. A spacecraft traveling at the Parker Solar Probe's top speed would arrive at Proxima Centauri long after every human civilization that has ever existed has risen and fallen multiple times over. This is a core engineering problem of interstellar travel, and it dwarfs every other challenge. The distance is not just large, it is large in a way that makes all of our existing propulsion technology essentially irrelevant. So what are the alternatives? Moving faster, the propulsion problem. If we want to reach Proxima Centauri in a time frame that is meaningful, say, within a few centuries rather than several millennia, we need to travel at a significant fraction of the speed of light, not necessarily 10% or 20%. Even 1% of the speed of light would be transformative. At 1% of light speed, the journey takes roughly 420 years. At 10%, it takes 42 years. The question is how to get there. There are several serious proposals in the scientific and engineering literature, and it is important to distinguish clearly between those that are theoretically grounded versus those that are more speculative. The first and most thoroughly studied concept is nuclear pulse propulsion. The basic idea, formalized in the late 1950s under a project called Project Orion, is to use a series of nuclear explosions detonated behind the spacecraft to generate thrust. Each explosion propels a pusher plate, which transfers momentum to the ship. The physics work. The engineering challenges are severe. Materials capable of surviving repeated nuclear blasts, the obvious political and international law complications of launching nuclear devices from Earth. But nuclear pulse propulsion is not a fringe idea. Project Daedalus, a detailed engineering study conducted by the British Interplanetary Society in the 1970s, proposed a variant using nuclear fusion rather than fission explosions, and concluded that a cruise velocity of approximately 12% of light speed was achievable in principle. A follow-up study, Project Icarus, revisited and refined these calculations more recently and reached broadly similar conclusions. 12% of the speed of light would get you to Proxima Centauri in approximately 35 years of ship time, though the deceleration problem, which Daedalus notably did not solve for a crewed mission, means the practical mission time would be considerably longer. The second serious concept is the laser-driven light sail. This is the basis of Breakthrough Starshot, an initiative announced in 2016 by a group of scientists and funded philanthropically. The idea is to build an array of ground-based lasers that collectively produce an extraordinary amount of focused energy, then use that energy to accelerate an extremely lightweight sail, potentially reaching 20% of the speed of light. A 2024 paper published in Nature Communications confirmed that flexible nanophotonic light sails based on silicon nitride membranes could, in principle, achieve the dynamic stability needed for laser-driven propulsion at relativistic speeds. The critical limitation of Breakthrough Starshot in its current formulation is scale. The technology as currently conceived is designed for gram-scale probes, essentially tiny chips with cameras. Scaling the concept to carry humans would require engineering solutions several orders of magnitude beyond what has been demonstrated or even seriously designed. A 2025 paper studying interstellar mission design using fusion-powered spacecraft for Proxima found that a fusion-driven rocket using deuterium, helium-3 fuel could achieve a slow flyby or bounded orbit around Proxima b with mission time of approximately 57 years. But again, this is theoretical, and the engineering gap between the calculation and the hardware is enormous. The third concept, and the one most relevant to a crewed mission carrying hundreds or thousands of people, is the generation ship, a spacecraft large enough and self-sufficient enough to sustain a human population across centuries of travel. This concept does not require exotic new propulsion physics. It requires making existing propulsion ideas work at large scale, and then solving the much harder problem of keeping people alive and psychologically coherent for hundreds of years. This is actually the most realistic option for a crewed interstellar mission in the view of many researchers who work in this area. Not because the engineering is easy, but because it does not depend on any breakthrough physics. It depends on better engineering of things we already understand: closed-loop life support, nuclear propulsion, artificial gravity, and human social organization. It is also, by far, the strangest and most philosophically difficult option, because a generation ship is not really a mission in the traditional sense. It is a civilization. Consider what you are actually proposing when you say generation ship. You are proposing that a group of human beings board a spacecraft knowing with certainty that they will never reach the destination. Their children will not reach the destination. Their grandchildren may not reach the destination. The people who eventually arrive, if the mission succeeds, will be the great-great-great-grandchildren of the original crew, separated from the founders by the same span of time that separates us from the early medieval period. Those people will have been born in space. They will have grown up in space. Their entire understanding of what it means to be human, what a sky looks like, what rain feels like, what it means to stand in a forest or swim in an ocean, all of that will be inherited knowledge, transmitted through language and image and tradition, but never experienced. And here's a question that sits at the center of all serious ethical discussions about generation ships. Do we have the right to make that choice for them? The people who board the ship choose to go. But the people born on the ship, the second generation, the third, the 10th, they made no such choice. They were born into a situation that was decided for them before they existed. Is that different, ethically, from the situation any of us are born into? Every person born on Earth is born into a world they did not choose, a culture they did not select, a set of circumstances imposed by the generations that came before. Some philosophers argue that the generation ship case is no different, that all life involves constraints we did not choose, and that being born into a purposeful voyage toward a new world is not inherently worse than being born into any other set of constraints. Others argue that the confinement is categorically different, that removing the possibility of leaving, of opting out of the mission, constitutes a kind of harm that cannot be undone. These debates are not resolved. They are ongoing, and they matter, because any serious interstellar mission planning process will have to confront them directly, not as abstract philosophy, but as concrete policy questions about what we are actually authorized to do on behalf of people who have not yet been born. Let's bring this back to something more concrete. The numbers. How many people do you actually need? This is a question that has received serious scientific attention, and the answers are more precise and more interesting than you might expect. The fundamental problem is genetic diversity. A small, isolated population that reproduces over many generations will experience what geneticists call genetic drift, a random loss of alleles from the gene pool, not because those alleles are harmful, but simply because chance determines which individuals reproduce and which do not. Over generations, genetic drift in a small population leads to what is called inbreeding depression, reduced fertility, increased susceptibility to disease, and the accumulation of harmful recessive mutations that will be suppressed in a larger, more diverse gene pool. We know what this looks like in practice. It is the same process that threatens isolated, endangered animal populations. It is the same concern that affects island communities cut off from mainland populations for centuries. The human genome carries a kind of memory of these events. population bottlenecks in our evolutionary history are detectable in modern human DNA. In 2017, astrophysicist Dr. Frederick Marin and particle physicist Dr. Camille Beluffy published a study using a Monte Carlo simulation model they called Heritage to calculate the minimum viable crew size for a multigenerational voyage to Proxima Centauri b. Their conclusion, under conservative assumptions, was that a minimum of 98 people would be required at departure to maintain a genetically healthy population across the journey. However, other researchers have challenged this number as too optimistic. The key variable is not just how many people you start with, but how genetic diversity is managed over time, who is allowed to reproduce with whom, whether frozen genetic material or embryos are carried to supplement diversity, and how many generations a journey takes. Anthropologist John Moore at the University of Florida argued that a multi-thousand-year voyage could be sustained with an initial crew of approximately 150, but subsequent analyses using more sophisticated modeling suggested this number was likely too low. In November 2024, Project Hyperion, an international design competition organized by the Initiative for Interstellar Studies, drawing participants from organizations including NASA, ESA, and MIT, launched a formal competition to design a crewed interstellar spacecraft. The competition specifications call for a ship capable of carrying between 500 and 1,500 people, a range that reflects the current scientific consensus that a genetically and socially viable interstellar colony requires at minimum several hundred individuals, not dozens. The winning design, announced in July 2025 and named Chrysalis, proposed a vessel that was conceptually 36 miles in length, a structure of a scale almost impossible to visualize, designed to sustain a traveling civilization across a journey of 250 years at a small fraction of the speed of light. Chrysalis incorporated artificial gravity through rotation, currently the only physically validated method for preventing the degenerative effects of prolonged weightlessness, and closed-loop life support systems for food, water, atmosphere, and waste processing. 250 years. That is 10 to 12 generations of human beings, depending on how you calculate generational length. It is the span of time between the American Revolution and the present day. The original crew would be as remote in time to the arriving colonists as George Washington is to us. And that raises one more question that we should sit with before closing this first part of our journey. What does a voyage like this do to a society? Humans evolved in small groups. The anthropological evidence suggests that the natural cognitive limit for stable human social groups is somewhere around 150 individuals, a number sometimes called Dunbar's number after the anthropologist Robin Dunbar who proposed it. Within that range, people can maintain genuine personal relationships with everyone in the group. Beyond it, you need formal institutions, laws, governance structures, hierarchies to maintain social cohesion. A generation ship carrying 1,000 people sits well above Dunbar's number, which means it needs real governance, real laws, real mechanisms for resolving disputes. And those mechanisms need to survive for 250 years, across at least 10 generations, in a closed environment from which there is no escape. History gives us very few examples of institutions that survive intact for 250 years. The Catholic Church, a handful of ancient universities, some constitutional systems, though usually with major revisions. The challenge on a generation ship is not just engineering a vessel that doesn't break down. It is engineering a society that doesn't break down. And societies are considerably harder to engineer than vessels. The researchers who study this problem, and there are now dedicated academic programs in what might be called generation ship social design, tend to emphasize two things. First, the population needs to be large enough and diverse enough in skills and temperament to handle crises that no one predicted. Second, the social structures established at departure need to be flexible enough to evolve, because a constitution written for the first generation may not serve the 10th generation well. There's also a psychological dimension that goes beyond social structure. Isolation studies, including research conducted on the International Space Station and in Antarctic research stations, consistently show that prolonged confinement in small groups produces specific psychological stressors, difficulty sleeping, increased anxiety, interpersonal conflict, a phenomenon called third quarter syndrome, where morale drops most sharply not at the beginning or the hardest moments of a mission, but in the psychological middle, when the end feels neither near nor inspiring. On a generation ship, the psychological middle might last for several entire human lifetimes. This is where we leave part one. We have established why this mission might be undertaken, not as romance, but as long-term species survival strategy combined with humanity's oldest drive toward the unknown. We have identified the most plausible destination and been honest about what we do not know. We have confronted the raw scale of the distance. And we have begun to see that the greatest challenges of interstellar colonization are not purely technological. They are biological, social, psychological, and philosophical in equal measure. In part two, we will go deeper into the ship itself, the propulsion, the radiation environment, what space actually does to the human body over decades and generations, and how engineers are currently thinking about keeping 1,000 people alive across the void between stars. Because the distance is only the first problem. What happens to you while you cross it is the second. There's a thought experiment that engineers and mission planners sometimes use when they want to communicate just how different interstellar travel is from everything we have done before. Imagine the most complex machine humanity has ever built. Most people, when asked, think of the International Space Station, a structure assembled over 13 years by 5 space agencies representing 15 nations, involving more than 40 assembly flights, containing roughly 1 million components, and continuously inhabited for over 25 years. It is genuinely one of the most extraordinary engineering achievements in human history. Now imagine that you need to build something more complex than that. Something that not only functions without failure for 250 years, but actively repairs itself, adapts to problems no one anticipated, grows food, recycles every molecule of water and air, generates its own energy, manages the health of 1,000 people across 10 generations, and does all of this while traveling through an environment more hostile than anything on the surface of Earth or in low Earth orbit. That is a generation ship, not a spacecraft in the traditional sense. A self-contained biosphere, a world that fits inside a hull. And before we get to problems of biology and psychology, which are real and severe, we have to start with the most fundamental question of all. How do you make the thing move? The engine problem. Let's be direct about something that often gets glossed over in popular discussions of interstellar travel. We do not currently have a propulsion system capable of sending a crewed spacecraft to another star in any reasonable time frame. Not close to having one. Not a few engineering iterations away from one. What we have are concepts, some more developed than others, some grounded in well-understood physics, some requiring technologies that do not yet exist in any form. Understanding the difference between these categories matters enormously if you want an honest picture of what interstellar travel actually requires. The most physically grounded concept, the one that depends least on future breakthroughs, is nuclear propulsion in one of its several forms. The underlying physics of nuclear reactions is not speculative. Nuclear fission and nuclear fusion both release energy at densities that are millions of times greater than chemical combustion, which is what all current operational rocket engines rely on. The question is not whether nuclear reactions produce enough energy for interstellar propulsion. They do, by a significant margin. The question is whether we can engineer a system that harnesses that energy efficiently enough, reliably enough, and safely enough to function as a spacecraft engine across timescales of decades or centuries. The most studied nuclear propulsion concept is nuclear pulse propulsion, the detonation of nuclear devices behind the spacecraft to generate thrust through the pusher plate mechanism. Project Orion in the late 1950s established that this concept was physically coherent, and the classified calculations from that period suggested that a spacecraft using nuclear pulse propulsion could achieve velocities between 3 and 10% of the speed of light. At 3% of light speed, the journey to Proxima Centauri takes approximately 140 years. At 10%, it takes approximately 42 years. Those numbers sound almost manageable, compared to the 6,300 years we calculated earlier for conventional propulsion. But they come with serious caveats. The engineering challenges of nuclear pulse propulsion are not trivial. The pusher plate, the component that absorbs the force of each nuclear detonation, must withstand repeated extreme mechanical and thermal shocks without failing. The detonation frequency required to sustain meaningful acceleration means the system must function reliably across tens of thousands of individual pulses. And the fuel mass problem, the sheer quantity of nuclear material required, is daunting. For a vessel carrying 1,000 people and supplies needed for a multigenerational crossing, the fuel mass alone would likely exceed the mass of everything else on the ship by a considerable factor. Project Daedalus, the British Interplanetary Society study from the 1970s, attempted to solve some of these problems by proposing a fusion-based variant, specifically using inertial confinement fusion with deuterium and helium-3 as fuel. The Daedalus study concluded that a cruise velocity of approximately 12% of light speed was achievable in principle, which would bring the transit time to Proxima Centauri to around 35 years for an uncrewed probe. A 2025 mission design study from Virginia Tech, analyzing a fusion-powered crewed mission to Proxima be using a fusion-driven rocket with deuterium, helium-3 fuel, found that a slow flyby or bounded orbit around the planet could be achieved with mission time of approximately 57 years. But notably, this study was exploring the theoretical design space, not proposing a vehicle that could be built today. There is a specific engineering complication with fusion propulsion that the Daedalus study candidly acknowledged, and that has not been resolved in the decades since. Helium-3 is extraordinarily rare on Earth. The moon's surface contains deposits of helium-3 implanted over billions of years by the solar wind, and some researchers have proposed mining the lunar regolith as a fuel source. The outer planets, particularly Uranus and Neptune, have been proposed as alternative sources, but neither of these is a near-term solution. Mining helium-3 from the moon or the outer planets at the quantities required for an interstellar mission would itself be an engineering project of civilizational scale. The laser-driven light sail concept, the basis of breakthrough Starshot, sidesteps the fuel problem entirely by leaving the energy source on Earth. A large array of ground-based lasers focuses its combined energy on a reflective sail, accelerating it to a significant fraction of the speed of light. Breakthrough Starshot's target is 20% of light speed, which would bring a probe to Proxima Centauri in approximately 20 years. A 2024 study published in Nature Communications confirmed that the dynamic stability problem, the tendency of the light sail to tumble or drift out of the laser beam during acceleration, can in principle be solved through careful nanophotonic design of the sail material. This is genuine scientific progress, but the scale problem remains categorical. Breakthrough Starshot is currently designed for probes that weigh grams. A generation ship weighs millions of kilograms. The laser array required to accelerate a crewed vessel to even a small fraction of light speed would need to be orders of magnitude more powerful than anything currently proposed, requiring an energy infrastructure that does not exist and cannot be built with present-day technology. This does not mean laser propulsion is irrelevant to the interstellar question. It may be the most practical near-term option for sending robotic probes ahead of any crewed mission, probes that could arrive at Proxima Centauri within a human lifetime and return data about the destination before the generation ship ever departs. This reconnaissance function is actually critical because, as we discuss in Part 1, the habitability of Proxima b is currently unknown. A crewed mission should not depart for a destination whose conditions are a mystery. Small laser-propelled probes could resolve that mystery decades in advance. What all of this means, taken together, is the following. The propulsion technology for an interstellar generation ship does not currently exist in operational form. It exists in detailed conceptual and theoretical form, and the physics underlying the most serious proposals is sound. The gap between the physics and the hardware is large, but it is an engineering gap rather than a scientific one, meaning there is no known law of physics that prevents it from being closed, only a very large amount of engineering work that has not yet been done. For our purposes, imagining how the first interstellar colony would actually function. We will proceed on the assumption that a generation ship traveling at somewhere between 2 and 5% of the speed of light is what eventually gets built, that give a transit time of between 85 and 210 years, depending on the specific velocity achieved. It is the most conservative scenario that is still physically plausible within the framework of nuclear propulsion, and it defines the time constraints within which every biological and social challenge must be solved. What space actually does to the human body. Here is a number worth knowing. As of 2025, only 24 human beings have ever traveled beyond Earth's protective magnetosphere, and the longest any of them stayed outside, it was approximately 12 days during the Apollo 17 mission. Every other human spaceflight in history has occurred within or close to the magnetosphere, which provides substantial protection against the radiation environment of deep space. We have never sent a human being into deep space for longer than 2 weeks. We are proposing to send 1,000 people into deep space for 2 centuries. The gap between our experience and our ambition is enormous, and the medical implications of that gap are only beginning to be understood. There are 2 primary physical hazards in deep space that have no good equivalent in Earth-based experience: radiation and the absence of gravity. Both of them cause damage to the human body. Both of them, if unaddressed, would likely make a multigenerational voyage impossible, and addressing them requires engineering solutions that are in very different states of development. Let's take radiation first. Radiation, the invisible architecture of harm. In deep space, beyond the protection of Earth's magnetosphere, the human body is exposed to 2 distinct categories of radiation that are qualitatively different from almost anything encountered on Earth's surface. The first is solar particle events, bursts of high-energy protons and other particles emitted by the sun during solar flares and coronal mass ejections. These events are intermittent and somewhat predictable, though not with enough precision to guarantee warning time. During a major solar particle event, the radiation dose received outside any shielding can be lethal within hours. Inside a spacecraft with water or polyethylene shielding, both of which are effective at blocking protons, the dose is reduced substantially, but the events still represent acute radiation hazard that requires careful management. The second, and in many ways more serious, category is galactic cosmic radiation, GCR. These are high-energy particles originating from outside our solar system, accelerated by supernovae and other energetic astrophysical events over billions of years. They include heavy ions, iron nuclei, silicon nuclei, and others, traveling at relativistic velocities. The distinguishing feature of galactic cosmic radiation is that it is omnidirectional, constant, and extremely difficult to shield against. The reason shielding against GCR is so difficult comes down to the physics of how these particles interact with matter. A high-energy heavy ion passing through a shielding material does not simply stop. It generates secondary radiation through a cascade of nuclear interactions. This means that beyond a certain thickness, adding more shielding material actually increases the total radiation dose received inside the shield, rather than reducing it. Water and polyethylene are among the best passive shielding materials identified, but they cannot reduce deep space GCR exposure to Earth normal levels using any practical amount of material. A 2025 review paper in the journal Fundamentals of Space Medicine and Clinical Technology summarized the current state of knowledge directly. Space radiation is one of the most significant health risks for long-duration missions, with cancer, cognitive decline, and cardiovascular disease among the primary documented concerns. The paper also noted that the biological effects of space radiation remain incompletely understood for extended exposure durations, because only 24 humans have ever been exposed to the deep space radiation environment, and none of them for longer than 12 days. What we do have is animal research and cellular research, and the findings from those studies are concerning in specific and measurable ways. Studies examining the effects of simulated galactic cosmic radiation on rodent brains have found persistent alterations in hippocampal neurogenesis, the generation of new neurons in the hippocampus, which is a brain region most associated with memory formation and spatial navigation. These alterations were observable months after exposure ended, suggesting that the effects are not transient but represent lasting changes to brain structure. Other research has found that galactic cosmic radiation causes persistent elevations in oxidative stress in cardiovascular tissues. A retrospective analysis of Apollo lunar astronauts, the only humans who traveled beyond Earth's magnetosphere for more than a few hours, found elevated rates of cardiovascular disease mortality compared to both non-astronaut controls and astronauts who flew only in low Earth orbit. This finding is not definitive evidence of causation, because the sample size of lunar astronauts is small and confounding factors are difficult to rule out. But it is a kind of preliminary signal that takes on significance when combined with the mechanistic findings from cellular and animal studies. For a generation ship crew, the cumulative radiation exposure over a lifetime in deep space would be many times greater than what any human being has ever received. Current models suggest that even with the best passive shielding available, crew members would receive radiation doses well above the limits that NASA currently enforces for astronauts in low Earth orbit, limits that are themselves set conservatively, based on a 3% increased lifetime cancer mortality risk. There are two broad approaches to this problem that researchers are currently exploring. The first is active magnetic shielding, using superconducting magnets to generate a magnetic field around the spacecraft that deflects charged particles before they reach the hull, in the same way Earth's magnetosphere deflects the solar wind. This concept is physically sound. Earth's magnetosphere works on exactly this principle. The engineering challenge is generating a field of sufficient strength and spatial extent to provide meaningful protection to a spacecraft crew using a magnet system that can function reliably for decades without maintenance. The energy requirements and the structural complexity involved are formidable, but several research groups consider active shielding the most promising long-term solution for deep space radiation protection, and work on the concept is ongoing. The second approach is biological, researching whether the human body's natural radiation repair mechanisms can be enhanced through pharmacological or genetic means to better tolerate deep space radiation exposure. A 2018 review paper laid out a roadmap for enhancing human radioresistance, including through upregulation of endogenous DNA repair mechanisms and exploration of gene therapy approaches. This line of research is in early stages, and the ethical questions around genetic modification of human beings for the purpose of space travel are substantial. But it represents a genuine area of scientific inquiry, not speculation. What does not appear to be a viable solution is simply ignoring the radiation problem and hoping that people will be fine. The evidence accumulated so far, while incomplete, consistently points in the direction that extended exposure to the deep space radiation environment causes measurable biological harm. Any serious generation ship design must treat radiation mitigation as a primary engineering constraint, not an afterthought. Gravity or the lack of it. The second major physical hazard is weightlessness, and the effects here are better documented than the radiation effects, because astronauts on the International Space Station have been experiencing them continuously for over 25 years. The human body evolved over hundreds of millions of years in a gravitational field of approximately 9.8 meters per second squared. Every system in the body is calibrated to that number. Bone density maintenance, muscle mass retention, cardiovascular function, fluid distribution, immune regulation, vision, all of them are affected when gravity disappears. In extended microgravity, bones lose density at a rate of roughly 1 to 2% per month in weight-bearing bones, even with aggressive countermeasures, including exercise. Muscles atrophy at a similar rate. The cardiovascular system, no longer required to pump blood upward against gravity, gradually deconditions. The heart becomes less efficient, and the body's ability to regulate blood pressure upon standing becomes impaired. Fluid shifts toward the head in microgravity, increasing intracranial pressure, and in some astronauts causing permanent changes to the structure of the eye and optic nerve, a condition called spaceflight-associated neuroocular syndrome, which has been identified as a significant medical concern for long-duration missions. The immune system also behaves abnormally in microgravity. Multiple studies have shown that latent herpes viruses, which most adult humans carry in a dormant state, reactivate in astronauts during spaceflight, presumably because immune surveillance is reduced, wound healing is delayed, inflammatory responses appear dysregulated. For a 6-month mission to the International Space Station, these effects are manageable. Astronauts exercise extensively to minimize bone and muscle loss, and most physiological changes reverse within months of returning to Earth. For a mission of decades in duration, let alone centuries, the situation is categorically different. The body cannot maintain countermeasures indefinitely against an environment it was not built for. And unlike ISS astronauts, generation ship inhabitants would never return to Earth. There is no recovery period. Space is where they live. The children born on such a ship would develop in an environment of reduced gravity from the moment of their birth. We have no data on what that does to a developing human body, because no child has ever been born in microgravity. The developmental biology of weightlessness in humans is entirely unknown. Animal studies in rodents suggest that development in microgravity produces measurable differences in bone structure and vestibular function. What the long-term effects in humans would be across multiple generations is genuinely uncertain in ways that should give serious pause to anyone designing this mission. This is why artificial gravity is not a luxury feature of a generation ship. It is a survival requirement. Artificial gravity, the rotation solution. There's exactly one method of generating artificial gravity that is validated by physics and does not require any speculative new technology. Rotation. When a structure rotates, anything inside it experiences a centrifugal force directed outward from the axis of rotation. If the rotation rate and the radius of the structure are correctly chosen, this centrifugal force can be made equivalent to Earth's gravitational pull. This is not simulated gravity or metaphorical gravity. It is real mechanical force that the body responds to in the same way it responds to actual gravity, because from the body's perspective, force is force. The physics were worked out long ago. The formula is straightforward. The centripetal acceleration experienced at the rim of a rotating structure equals the radius multiplied by the square of the angular velocity. To produce one Earth gravity at a rim radius of 250 meters, you need a rotation rate of approximately 1.9 revolutions per minute. At 500 meters, the required rotation rate drops to about 1.3 revolutions per minute. The reason radius matters is that at small radii and high rotation rates, the human vestibular system, the inner ear's balance and orientation sensing mechanism, begins to experience what is called the Coriolis effect, a perceived force that acts on moving objects in a rotating reference frame. At high rotation rates in small structures, this Coriolis effect causes disorientation, nausea, and motion sickness. Research suggests that most people can adapt to rotation rates below about 2 revolutions per minute, but beyond that, the proportion of people who experience persistent disorientation increases significantly. This means a practical artificial gravity system requires a large structure, hundreds of meters in radius at minimum, rotating slowly, which is consistent with the scale already required for a generation ship on other grounds. A vessel carrying 1,000 people for 2 centuries needs to be large for many reasons, and artificial gravity requirements are simply one more constraint pointing in the same direction. The 2024 Project Hyperion competition specifications explicitly required artificial gravity through rotation as a design constraint, and the winning Chrysalis design incorporated this feature. It is worth noting that this is one area where the science is settled, not a hypothesis, not a research program, but a physically validated engineering requirement with a known solution. The challenge is building a structure of sufficient scale, not understanding the physics. Closed-loop life support, eating, breathing, drinking, and not dying. A generation ship cannot carry 2 centuries of food, water, and oxygen as stored supplies. The mass would be prohibitive by many orders of magnitude. Every molecule of consumable resource on board must be recycled, regenerated, or grown. This is what is meant by a closed-loop life support system, a system in which the outputs of one process become the inputs of another, with nothing lost or waste. The concept is not exotic. It is what Earth's biosphere does on a planetary scale, all the time. The question is whether it can be engineered at the scale of a spacecraft hull, with the reliability and redundancy needed to function without catastrophic failure for 200 years. The International Space Station operates a partially closed life support system. Water is recovered from astronaut urine and humidity in the cabin air and recycled back into drinking water and electrolysis-generated oxygen. The system is effective enough that NASA reports water recovery rates above 90% on the ISS. Carbon dioxide is removed from the cabin air and either vented or processed. But the ISS system is not a fully closed loop. It requires resupply of materials that cannot be recovered or generated on board, including food. Food on the ISS comes entirely from Earth. The microbial cultures and chemical processes that handle waste on the ISS are maintained through regular equipment replacement. For a generation ship, none of these options exist. The most serious approach to food production in a closed system involves bioregenerative life support, using living organisms, primarily plants and certain microorganisms, to convert waste products and sunlight or artificial light into food. Plants absorb carbon dioxide and water, use light energy to drive photosynthesis, and produce oxygen and edible biomass. Their root systems interact with microbial communities in the growing medium that break down complex organic waste into nutrients the plants can absorb. In a closed system, the plants feed the people's waste feed the plants, and the loop continues. A 2005 review paper published in Advances in Space Research identified bioregenerative life support as the only viable approach for long-duration deep space missions, noting that no purely physical-chemical system could provide all the functions needed without biological components. The research program for bioregenerative life support has made significant progress in the decades since, but has not yet been demonstrated at the scale required for a generation ship crew, and the stability of closed biological systems over timescales of decades or centuries has not been experimentally validated. The specific challenges are numerous. The microbial ecosystem in a closed life support system will inevitably evolve over time. Bacteria and fungi will mutate, communities will shift in composition, and the system behavior will change in ways that are difficult to predict. Managing this evolution without external input and without the microbiological expertise that resides in the scientific community on Earth requires either extraordinary monitoring systems and AI-assisted management, or the continuous cultivation of the relevant expertise within the ship's population across generations. Water recycling at the generation ship scale is better understood than food production. The physics of water purification, distillation, filtration, reverse osmosis, ultraviolet sterilization, are all well established, and the ISS experience provides a meaningful operational baseline. The primary engineering challenge is reliability over 2 centuries, ensuring that no single component failure cascades into a water supply crisis, which requires extensive redundancy and the ability to fabricate replacement components from materials available on board. Atmospheric management, maintaining the right balance of oxygen, nitrogen, carbon dioxide, and trace gases while managing humidity and removing contaminants, is similarly well understood in principle, though the long-duration reliability challenge applies here as well. One aspect of closed-loop life support that receives less public attention, but is critical to the mission, is the management of trace contaminants. Human beings are prodigious producers of volatile organic compounds, from off-gassing materials, cooking, body chemistry, and industrial processes. In an enclosed environment over decades, these compounds can accumulate to levels that affect health and cognitive function. The air quality management systems of a generation ship need to handle not just the major atmospheric gases, but the entire chemical complexity of a human habitation environment continuously for 2 centuries. Medicine across 2 centuries. One of the more sobering aspects of interstellar mission planning, and one that does not often receive the attention it deserves, is medicine. A generation ship crew of 1,000 people over 2 centuries will experience essentially everything that medicine deals with on Earth. Cardiovascular disease, cancer, infections, including infection by pathogens that may evolve over the course of the mission in ways we cannot predict, appendicitis, broken bones, difficult childbirths, mental illness, neurodegenerative disease, surgical emergencies. All of this must be managed by the medical resources and expertise available on the ship, with no possibility of consultation with Earth beyond the fundamental constraint that radio signals travel at the speed of light. And once the ship is, say, 50 light years into a journey, a radio message to Earth takes 50 years to arrive and another 50 years for a response to return. This means the ship's medical capability must be comprehensive, self-sustaining, and educationally self-perpetuating. The medical knowledge base cannot be allowed to degrade across generations. Every generation must include individuals trained in surgery, internal medicine, obstetrics, psychiatry, oncology, and every other medical specialty that a community of 1,000 people requires. That training must happen on the ship, using the ship's resources, taught by the previous generation. The knowledge management problem, ensuring that critical technical knowledge is not lost as generations turn over, is one of the most underappreciated challenges of multigenerational space travel. In the history of isolated human communities on Earth, specialized knowledge has been lost within as few as 3 generations when social conditions made it no longer immediately useful or when the people who carried it died before fully transmitting it. A generation ship cannot afford for that to happen with anything from medicine to materials engineering to reactor maintenance. Some researchers have proposed that artificial intelligence systems could serve as a persistent institutional memory for the ship, a continuously accessible repository of human knowledge that does not depend on any individual being alive to transmit it. This is a plausible and potentially important function, but it creates its own dependencies. The AI systems must be maintained, updated, and understood by each generation, which is itself a form of knowledge that must be transmitted. The psychological architecture of the crossing. Now we reach what many researchers consider the hardest unsolved problem of multigenerational space travel. Not the propulsion, not the radiation shielding, not even the life support. The psychology. Human beings are not built for the situation a generation ship puts them in. Every element of the evolved human psyche that has been studied tells us that certain things are important for psychological health. Connection to a natural environment, freedom of movement, the ability to choose one's social relationships, access to diverse social groups, a sense of meaningful personal agency, and, perhaps most fundamentally, the ability to imagine a different future for oneself. A generation ship constrains all of these. The environment is entirely artificial. Movement is constrained to the interior of the hull. Social relationships are limited to the same 1,000 people or their descendants, indefinitely, and personal agency over one's fundamental life situation, where you are, whether you can leave, is essentially zero. You were born there. You will die there. The mission continues regardless of what you personally think about it. The psychological literature on isolation and confinement provides some insight into what this might produce, though all existing analogs are vastly shorter in duration than an interstellar voyage. Research on ISS crew members, Antarctic winter-over teams, and submarine crews consistently identify specific challenges. Difficulty with interpersonal conflict in small groups that cannot be escaped, disruption of circadian rhythms, cognitive dulling, and a phenomenon known as third-quarter syndrome, a drop in morale and motivation that occurs not at the beginning of an ordeal, but roughly 3/4 of the way through, when the end feels neither near enough to motivate nor far enough. A way to have been normalized. On a generation ship, the 3/4 point of a 250-year voyage falls at roughly the 190-year mark. Most of the people experiencing third-quarter syndrome at that point will have been born on the ship, will have lived their entire lives on the ship, and will die on the ship without ever reaching the destination. The psychological challenge of maintaining motivation and purpose in that population, people who are living and dying in the middle of someone else's project, is profound and has no good historical analogy. Various proposed solutions exist in the generation ship design literature. Some researchers emphasize the importance of giving shipborne generations genuine political and social agency. the ability to make decisions about their own governance and culture, rather than simply inheriting a structure designed by the founding generation. Others propose that the ship should be large and varied enough that different communities can develop different cultures and social structures within the larger vessel, providing the diversity of social experience that small groups cannot. Some proposals involve deliberately limiting what subsequent generations are told about Earth and the destination, to prevent them from experiencing the psychological weight of comparison to a world they cannot reach. That last proposal, it should be said, raises its own ethical questions. The right of each generation to accurate information about their own situation is not a trivial matter. What the research consistently suggests is that the psychological design of the mission, the social architecture, the governance structure, the way meaning and purpose are cultivated across generations, is as important to mission success as the engineering design of the hull or the life support system. A ship that keeps its passengers physically alive but psychologically broken has not succeeded. The mission requires both. There is something worth pausing on here before we close the second part. We have spent this portion of our journey going deep into machinery of survival, propulsion, radiation, gravity, food, medicine, psychology. We have treated these as engineering problems to be solved, which they are, but underneath all the calculations and design parameters is something that is harder to put in a technical document. The people on this ship, the founders who board it, and every generation that follows, will be doing something that no human being has ever done. They will be living and dying in a darkness so total that the nearest star is years of light travel away in every direction. They will raise children in that darkness. Those children will raise children. The darkness will be the only world most of them ever know. And the question of how a human being finds meaning in that situation, how a society maintains not just its biological continuity, but its humanity, its curiosity, its creativity, its capacity for joy, is not an engineering question. It is a philosophical one, and it does not have a clean answer. What we can say is that human beings have found meaning in circumstances that looked, from the outside, incompatible with any reasonable expectation of flourishing. Isolated communities, extreme environments, terrible historical circumstances. And in many of those situations, culture persisted, art was made, children were loved, and people found ways to live with dignity. A generation ship would be an extreme version of this, but perhaps not a categorically different one. In part 3, we will reach the destination. After 2 centuries of crossing, after the generations of people who managed a reactor and grew the food, and resolved the disputes, and raised the children, and died in the darkness between stars, the ship will decelerate, and a world will appear that no human being has ever stood on. What waits there? How you build a colony in a place that may or may not be capable of supporting life. How you go from 1,000 people in a hull to a civilization on a new world. And what it means, finally, for our understanding of what it is to be human, not on Earth, not in the solar system, but elsewhere in the galaxy. That is where we're going next. 250 years. 10 generations of human beings have been born, have lived full lives, and have died inside this ship. The founding crew, the people who made the choice, who said goodbye to Earth, who watched the sun shrink to a point of light indistinguishable from the other stars. None of them are alive anymore. They have not been alive for a very long time. Their names are known the way we know the names of historical figures, through records, through stories passed down, through the institutional memory of community that has been carrying their decision forward across 2.5 centuries. The people alive now, the generation that will actually arrive, were born into this mission. They did not choose it. They have never known anything else. And now, for the first time in the ship's history, something is changing. The sensors are registering it. The navigation systems are confirming it. The dim red point of light that has been growing, almost imperceptibly, in the forward observation screens of the past several decades is no longer a point. It has become a disk. Proxima Centauri, a star so small and cool that it produces only about 0.0017% of the luminosity of our sun, is now visible as something with actual shape and dimension, and orbiting it at a distance of roughly 7.5 million kilometers is a world. Let's begin where the mission itself begins at this moment, with the question of what you are actually looking at. What arrives at Proxima Centauri b? By the time a crew generation ship reaches Proxima Centauri, we can assume, reasonably, that humanity will have sent robotic probes ahead of it, laser-propelled light sails, traveling at 20% of the speed of light, could have reached the system decades before the generation ship and transmitted detailed observational data back to Earth, and by relay to the ship itself. What the arriving colonists find should not be a complete surprise. They should know the basic atmospheric composition. If an atmosphere exists, they should have surface temperature maps. They should have a reasonable picture of what they're descending into. But there's a limit to what remote observation can establish, even at close range. And so the first question the arriving crew must answer, in real time, with the instruments on board, and eventually with direct measurement, is the habitability question we left open in Part 1. Is Proxima Centauri be a world that can support human life, even in a heavily modified and engineered form? Or is it a radiation-scoured, airless rock? The honest answer, as of what science currently tells us, is that we do not know, and the arriving colonists will be discovering the answer for themselves. Let us walk through what we currently understand about the environment they would encounter, being precise about what is confirmed, what is debated, and what is simply unknown. The star itself. Proxima Centauri is an M dwarf, a red dwarf star, with a surface temperature of approximately 3,042 Kelvin, compared to our Sun's roughly 5,778 Kelvin. It is approximately 12% the mass of our Sun, and about 14% its diameter. In terms of raw luminosity, it produces a tiny fraction of the energy our Sun produces. This means that Proxima b, despite orbiting at a distance of only about 7.5 million kilometers, compared to Earth's 150 million kilometers from the Sun, receives an energy input from its star that is broadly comparable to what Earth receives from the Sun, roughly 65 to 70% of Earth's solar constant. According to the original discovery paper published in 2016, this is within the range where liquid water is theoretically possible on the surface, which is the basis for the habitable zone classification. But the nature of M dwarf stars creates complications that do not have analogs in Earth's situation around a G-type star like our Sun. First, Proxima Centauri is significantly more magnetically active than our Sun, particularly in its emission of X-ray and ultraviolet radiation. Studies have measured that Proxima b currently receives approximately 30 times more extreme ultraviolet radiation and roughly 250 times more X-ray radiation than Earth receives from the Sun. These are not small differences. They represent a fundamentally different radiation environment at the planetary surface, with significant implications for any life, or any human habitation, on that surface. Second, Proxima Centauri produces frequent, powerful stellar flares. Sun releases a magnetic energy that generate intense bursts of radiation across the electromagnetic spectrum, from X-rays through ultraviolet to radio waves. In 2016, the same year Proxima b was announced, astronomers recorded an exceptionally powerful flare from Proxima Centauri that briefly increased the star's brightness by a factor of roughly 1,000 in the ultraviolet. Events of this magnitude, occurring regularly over geological timescales, would have profound effects on any planetary atmosphere, stripping it away if it lacks sufficient protection, or driving complex photochemical reactions if it retains one. Third, the gravitational dynamics of the system are unusual. Proxima b orbits so close to its star that tidal forces are likely significant. The current scientific consensus, based on orbital mechanics modeling, is that Proxima b is probably tidally locked to its star, meaning one side of the planet permanently faces a star in permanent daylight, while the other side faces away in permanent darkness. This is analogous to how our moon always shows the same face to Earth. A tidally locked planet has a dramatically different climate structure than a rotating planet like Earth. The day side could be very hot, the night side extremely cold, with a narrow terminator zone between them where temperatures might be more moderate. Whether a tidally locked planet can maintain habitable surface conditions is an open question in planetary science. Some atmospheric modeling studies suggest that a sufficiently thick atmosphere could redistribute heat from the day side to the night side efficiently enough to prevent the night side from freezing solid and the day side from boiling off the atmosphere. A 2024 study found that the presence of ozone in Proxima B's atmosphere would significantly affect its temperature distribution and atmospheric circulation, suggesting that the photochemistry of the atmosphere is a key variable in whether temperate conditions can be maintained anywhere on the surface. The 3:2 spin-orbit resonance is also possible, where the planet rotates 3 times for every 2 orbits, as Mercury does in our solar system. This will eliminate the permanent day and night sides, but the scientific literature currently considers synchronous rotation more probable for Proxima B's specific orbital parameters. The magnetic field question. The question of whether Proxima B has a magnetic field is, arguably, the single most important unknown in the habitability assessment, more important even than the atmospheric composition question, because a magnetic field determines whether an atmosphere can survive over geological timescales. Earth's magnetic field is generated by convective motion of liquid iron in its outer core, a dynamo driven by the planet's internal heat and its rotation. This field deflects the solar wind, the continuous stream of charged particles flowing outward from the sun, and protects the atmosphere from being gradually eroded by that particle flux. Without Earth's magnetic field, solar wind erosion over billions of years would likely have stripped our atmosphere to a fraction of its current density, as appears to have happened to Mars after its dynamo shut down roughly 4 billion years ago. The question for Proxima B is whether its interior is still hot enough and its rotation fast enough to sustain a similar dynamo. Tidal locking complicates this. A tidally locked planet rotates very slowly relative to its orbital period, which generally suppresses dynamo activity. Some researchers argue that this makes a Proxima B magnetic field unlikely. However, a 2025 study introduced a competing view, suggesting that Proxima B might generate a magnetic field through a mechanism driven by its liquid iron core, independent of rapid rotation. If confirmed, this would dramatically improve the habitability outlook. The key word is if confirmed. This remains a hypothesis based on interior modeling, not a direct measurement. What can be said clearly is this. The presence or absence of a magnetic field at Proxima B will be one of the first things the arriving mission needs to determine, because it conditions everything else about the colonization strategy. A planet with a magnetic field and a retained atmosphere presents one set of challenges. A planet without either presents a categorically different and more severe set of challenges, one where surface habitation, in any form resembling open-air access to the environment, may not be possible at all. 3 scenarios for what the colonists find. Rather than presenting a single picture of Proxima B's surface conditions, which would require choosing one hypothesis as true when the science does not support that choice, it is more honest to lay out the range of plausible scenarios that current scientific understanding permits, and to describe what each would mean for the colony. Scenario 1, a retained atmosphere, functional magnetic field, surface liquid water in some regions. In this scenario, Proxima B has followed what researchers call the habitable evaporated core pathway. It formed with a volatile-rich interior, survived the intense early radiation of young Proxima Centauri with some combination of atmospheric replenishment and magnetic protection, and arrived at its current age with thin to moderate atmosphere, possibly containing nitrogen, carbon dioxide, water vapor, and potentially oxygen if geological or biological processes have produced it over billions of years. In this scenario, the terminator zone, the boundary between the permanent day and night sides, might support surface temperatures within the range of liquid water, particularly if atmospheric circulation distributes heat with reasonable efficiency. The surface radiation environment would still be significantly more intense than Earth's, particularly during stellar flares, but it would be manageable with shielding. This is the most optimistic, realistic scenario. It does not mean the surface is pleasant or immediately habitable without infrastructure. It means that the fundamental physical constraints do not rule out surface habitation in principle, and that with appropriate engineering, a colony could potentially access the natural environment of the planet rather than being permanently sealed inside artificial structures. Scenario 2, a thin atmosphere, marginal magnetic field, extreme surface conditions but accessible resources. In this scenario, Proxima b has retained some atmosphere, but not enough to provide meaningful radiation shielding or to maintain liquid water at the surface, except perhaps in deep geological formations. The magnetic field is present but weak, providing partial protection against stellar wind erosion, but not stopping it entirely. Surface temperatures in the terminator zone might be below freezing, with the day's side too hot for liquid water and the night side too cold. This scenario, which many planetary scientists consider the most probable based on current modeling, would preclude open surface habitation, but would not preclude underground or subsurface habitation, where the rock above provides radiation shielding and thermal regulation. It would require that all colonist activity happen either inside pressurized surface structures with radiation shielding built in, or in excavated underground facilities. Water might be accessible as subsurface ice, particularly on the night side, mineable through drilling. This is a harder scenario than the first, but it is not an impossible one. It is roughly analogous, in broad terms, to what a Mars colony would face, though the specific parameters of Proxima b would be different. Scenario 3, no meaningful atmosphere, no magnetic field, a radiation environment hostile to surface activity. In this scenario, the early XUV radiation from young Proxima Centauri strip away any atmosphere Proxima b may have once possessed, and without atmospheric pressure or magnetic protection, the surface is directly exposed to stellar radiation and cosmic radiation simultaneously. The surface temperature distribution follows the stellar irradiation directly, with the day side reaching temperatures potentially high enough to melt certain minerals and the night side at cryogenic temperatures. In this scenario, the surface of Proxima b is genuinely uninhabitable in any conventional sense. No amount of engineering produces an open surface colony. Any human presence on or near the planet requires deep underground facilities carved into the rock, entirely self-contained, using the planet essentially as a source of raw materials and radiation shielding while conducting no meaningful biological interaction with the surface environment. This scenario is not ruled out by current science. It may, in fact, be the most likely scenario for some planetary scientists who weight the radiation stripping evidence heavily. If it is what the arriving colonists find, the colony they build will look more like a mining operation carved into an airless rock than anything resembling the establishment of a new Earth. Landing, regardless of which scenario the colonists encounter, the physical process of getting from the ship to the surface is its own engineering challenge. The generation ship, after 2.5 centuries of travel, arrives in the Proxima Centauri system at a velocity that must be decelerated to orbital velocity before any descent can be attempted. The deceleration maneuver, which requires as much energy as the original acceleration, and must be executed using fuel carried on board or harvested from the interstellar medium during the cruise phase, is one of the major unresolved design problems for any crewed interstellar mission. Project Daedalus, which was designed as an uncrewed flyby probe, explicitly did not solve the deceleration problem. For a crewed mission, deceleration is not optional. Once in orbit, the colonists face another challenge. They have spent their entire lives, or their ancestors have spent theirs, in artificial gravity produced by a rotating ship structure. The surface gravity of Proxima b is uncertain, but its minimum mass of 1.3 Earth masses suggests surface gravity likely somewhat higher than Earth's, possibly between 1.0 and 1.3 g, depending on the planet's actual composition and density. This is within the range a human physiology can handle, though transition from a rotating hull artificial gravity environment to real planetary gravity would require a physiological adaptation period. The colonists would need landers capable of descending through whatever atmosphere exists, or, in the absence of meaningful atmosphere, capable of controlled rocket descent to the surface. The landers would carry the initial surface infrastructure, habitat modules, power generation equipment, resource extraction tools, and communication systems. The first humans to stand on the surface of Proxima Centauri will be doing something that no member of our species has ever done, standing on solid ground that formed around a different star. The rock beneath their feet will be made of the same elements as Earth rock: silicon, iron, oxygen, magnesium, because the universe makes planets in the same periodic table everywhere. But it will be genuinely alien rock, never touched, never walked on, never shaped by any life or by any intelligence before that moment. What that moment means philosophically and emotionally for people who are born on a ship and have never stood on any ground at all, it is difficult to even imagine. Building the colony, the first 100 years on the ground. Let us now think carefully about what establishing a colony actually requires in operational terms, starting from the moment the first landers touched down. The colonists arrived with approximately 1,000 people, the number that has been sustained across the voyage, and whatever physical resources a ship carried from Earth, and potentially supplemented with materials mined during transit. They have no supply chain. No reinforcement are coming for any practical purpose, because the communication lag to Earth is 4.24 years each way, and any physical assistance from Earth will require another interstellar mission taking centuries to arrive. They are, for all operational purposes, entirely on their own. The first priority is shelter. Whatever the surface conditions, the colonists cannot survive exposed to the Proxima B environment without protection. In the most optimistic scenario, pressurized surface habitats with radiation shielding allow relatively comfortable surface existence. In less optimistic scenarios, the first construction project is the excavation of underground living spaces, using whatever drilling and tunneling equipment was brought from the ship or can be fabricated from local materials. The second priority is power. The generation ship presumably carries nuclear reactors. Any vessel capable of interstellar travel must have nuclear power sources, and some of those reactors can presumably be adapted for surface power generation. Solar power from Proxima Centauri is also potentially available, though the star's small size and spectral characteristics mean that solar panels optimized for Earth's sun will be less efficient at Proxima Centauri's output spectrum. Research into photovoltaic optimization for M-dwarf stellar spectra is an active area of work precisely because of its relevance to potential colonization of planets around red dwarf stars. The third priority is water and atmosphere. If water exists on Proxima B in any accessible form, surface ice, subsurface ice, mineral-bound hydrates, its extraction and purification become the foundation of the colony's long-term viability. Water is not just for drinking. It is the raw material for oxygen generation through electrolysis, for hydrogen fuel, and for radiation shielding. A colony with reliable water access has options. A colony without it faces an existential constraint from the first day. Atmospheric resources, assuming any atmosphere exists, provide nitrogen and carbon dioxide that can be used in greenhouse structures for plant growth, and potentially oxygen if the atmospheric composition permits. If the atmosphere is too thin or too hostile to harvest directly, the colonists must rely entirely on the closed-loop life support systems they operated on the ship, now transferred to a planetary surface context. Food production on the surface, or underground, follows the same bioregenerative principles discussed in Part 2. The fundamental advantage on the planetary surface, compared to the ship, is access to genuine regolith, planetary rock that can be processed into growing medium, supplementing or eventually replacing the carefully maintained soil ecosystems that sustain the ship population for 2.5 centuries. Whether Proxima B's regolith contains the mineral profiles useful for plant growth, and whether it contains harmful compounds that would need to be removed, is unknown and would need to be characterized in the early years of the colony. The genetic question revisited. A colony of 1,000 people is, genetically speaking, a small founding population. We discussed the minimum viable crew numbers in Part 2, but the colonization phase reframes this question in a different way. On the ship, genetic diversity could be managed actively through social norms around mate selection, through stored genetic material if the mission carried frozen embryos or gametes, through careful monitoring of the population's genetic health metrics across generations. The ship's population had the advantage of being a defined, stable group with known genetic profiles. On the planetary surface, the dynamics change. The colony will grow, reproduction in a new environment, with access to actual ground and resources beyond the ship's constraints, may proceed more rapidly than during the voyage. Population growth is actually necessary. A colony of 1,000 people is not a stable long-term civilization. The sustainable carrying capacity of even a resource-limited colony must ultimately be much larger to support the diversity of skills, knowledge, and social functions that a civilization requires. But growth from a small founder population, without genetic input from Earth for centuries, accumulates the same risks over time that we discussed for the ship population: genetic drift, inbreeding depression, the accumulation of harmful mutations. The long-term genetic health of the colony requires either very careful management of reproductive patterns, which raises profound questions about individual freedom, or some form of ongoing genetic supplementation. One approach that some researchers have proposed is the use of artificial reproductive technologies combined with frozen genetic material from Earth, essentially a genetic library carried on the ship, containing the genomic diversity of a much larger population than 1,000 people who actually made the journey. Frozen embryos, frozen gametes, or simply frozen DNA that can be used in assisted reproduction. All of these could expand the effective genetic diversity of the founding population far beyond what 1,000 living people represent. This is a real and serious proposal in the generation ship literature, not a speculative or frivolous one. Its ethical dimensions are substantial, particularly regarding the rights and identity of children born from this process, but its biological rationale is sound. The alternative, allowing the colony to grow naturally from its founding population with no supplementation, carries real risks of genetic decline over the centuries. These risks would not be immediately visible in the first generation of colonists, but would accumulate in the background of the gene pool and potentially manifest as reduced fertility, increased congenital disease rates, and reduced immune diversity in later generations. Managing this risk is not optional for a colony that intends to survive indefinitely. Governance, culture, and the question of identity. A colony of 1,000 people that must survive and grow on an alien world needs governance, formal structures for making collective decisions, resolving disputes, allocating resources, and managing the inevitable conflicts that arise in any human community. What governance structure is appropriate for the first interstellar colony is a genuinely open question, and the answer is likely to evolve significantly over the first century of surface habitation. The social structures that worked on the ship, designed for a defined population with defined mission in a closed environment, may not translate directly to a planetary surface context where the colony is expanding, where new roles and economic activities are emerging, and where the mission is no longer survive the crossing but build a civilization. One of the most interesting questions in the generation ship and colonization literature concerns cultural continuity and cultural evolution. The colonists will carry the culture of Earth, or more precisely, the culture of whatever portion of humanity launched the mission, filtered through 2.5 centuries of shipboard adaptation to Proxima B. But they will also be building something new. The environment will shape the culture. People who have grown up knowing that the radiation environment outdoors is hostile will develop a different relationship to the concept of outside than people who grew up on Earth where outdoors is generally safe. People who know that their water supply depends on careful management and that their food production is a life-critical system will develop a different relationship to resource management than people who grew up in societies with abundant and apparently infinite resources. The children born on Proxima B, the first generation to be native to another star system, will be different from their parents in ways that extend beyond culture. They will have developed in a different gravitational environment, under a different stellar spectrum, in a different atmospheric composition if the colony has transitioned to a locally sourced atmosphere. Their microbiomes, the communities of microorganisms that inhabit the human body and play critical roles in immune function, digestion, and possibly cognition, will have been shaped by the Proxima B environment rather than Earth's. Over generations, these differences will accumulate. The people of Proxima B will be human. They will share DNA, biology, language in some form, and probably culture in recognizable form. But they will also be, in subtle and in less subtle ways, different. Not a different species. At least not for a very long time. But a different population, shaped by a different world. The communication problem. There is one aspect of the colony's relationship with Earth that deserves careful attention because it defines the psychological and political context of the colonists' existence in a fundamental way. Radio signals travel at the speed of light. The distance between Proxima Centauri and Earth is 4.24 light years. This means that any message sent from Proxima B to Earth takes 4.24 years to arrive. A reply takes another 4.24 years to return. A single exchange of messages, a question and its answer, takes more than 8 years. This is not a communication delay in the ordinary sense. It is a delay that fundamentally changes the nature of the relationship. The colonists cannot have a conversation with Earth. They cannot ask for advice and receive it in time to act on it. They cannot participate in Earth politics, Earth culture, or Earth science in any direct way. By the time they receive news of an event on Earth, that event is more than 4 years in the past. By the time Earth receives their response, more than 4 years have passed again. The colony is, in a very real sense, alone. Not in the poetic sense of feeling isolated, but in the practical sense that every decision they make, every crisis they face, every choice about how to build their society, all of it must be made by the colonists themselves, with the resources and knowledge they have on hand. Earth can send information, libraries of scientific knowledge, cultural archives, software updates, genetic data. All of these can be transmitted as electromagnetic signals and received at the colony. And the colony can send information back. Scientific observations of Proxima B and its system, reports on the colony's development, data on the health effects of the planetary environment. The two civilizations will maintain a slow-motion dialogue that spans decades. But that dialogue cannot substitute for the colony's political and social self-sufficiency. The colonists cannot be governed from Earth. They cannot be economically dependent on Earth. They cannot wait for Earth's permission to make decisions that affect their survival. This is, in the long run, the most philosophically significant fact about the first interstellar colony. It will be the first human society that is genuinely, structurally independent of all other human societies. Not politically independent in the way that nations are independent of each other while existing on the same planet and maintaining daily contact. Structurally independent, operating across a communication barrier that makes real-time governance, real-time economic exchange, and real-time cultural participation impossible. Whether that independence is experienced as liberation or as loneliness, probably both at different moments by different people, it represents a genuinely new form of human existence. What this means for us. We began this journey with a practical question: how would humans actually survive in deep space and establish a colony around another star? And we have followed that question through propulsion physics, radiation biology, closed-loop ecosystems, genetic mathematics, social design, and planetary science. What we have found is not a simple answer. The question does not have one. What we have found is a picture of extraordinary complexity, a challenge that engages every field of human knowledge simultaneously, that requires solutions to problems that have never been solved before, and that cannot be reduced to any single technological breakthrough or any single act of will. Nuclear propulsion can close the energy gap in principle. Artificial gravity through rotation can keep bodies healthy in principle. Bioregenerative life support can feed and breathe 1,000 people for 2 centuries in principle. Careful genetic management can preserve the colony's biological viability across generations. In principle. In principle. Always in principle. The distance between principle and operational reality across every one of these domains is measured in decades of engineering work, billions in investment, and an institutional commitment that must survive political changes, economic fluctuations, and the simple human tendency to prioritize the immediate over the distant. But here is what is also true. Every technology described in this video as currently theoretical was, at some earlier point in history, not even theoretical, it was unimaginable. The ability to fly was considered impossible until it was not. The ability to split the atom was unknown until it became the defining fact of the 20th century. The ability to sequence the human genome was considered a project of impossibly vast scope until it was completed. The history of science and engineering is, in a sense, a history of the continuous revision of what counts as impossible. The generation ship is not impossible. The interstellar colony is not impossible. They are extraordinarily difficult. They require capabilities we do not yet fully possess. They raise ethical questions we have not yet resolved. They demand a scale of commitment and coordination that human civilization has rarely sustained. But none of that is the same as impossible. And there's one more thing worth saying, and perhaps it is the most important thing. The people who would actually do this, the people who would spend their entire lives crossing the void, who would be born and die inside a hull they never chose, who would be the first to stand on ground orbiting a different star, would not be doing it because of propulsion physics or genetic modeling or bioregenerative life support calculations. They would be doing it for the same reason that the first people crossed the Bering Land Bridge into an unknown continent, for the same reason that the first Polynesian navigators sailed into the open Pacific without knowing what lay on the other side, for the same reason that every human migration in history happened before anyone could calculate the odds with any precision, because something in the human animal is not satisfied with the known, because the horizon has always mattered, even when, especially when, it offers no guarantee of anything good waiting beyond it. The first interstellar colonists will not be braver than us. They will not be smarter than us. They will be human beings with all the fear and hope and confusion and love and conflict and creativity that the phrase human beings has always implied. They will just have a very long way to go. And maybe if we do the hard work of solving the problems described in this video, honestly, carefully, without shortcuts, they will actually get there